Hello everyone, and welcome to the first episode of Oxygen Not Included tutorial how to make a rolling display. First, let's take a look at the display in action. After typing the letters in the keyboard above, the display below outputs those letters column by column. Here you are seeing the words Hello World, of course. We can also switch the input to display other text. So how do we actually build a display like this? We'll break it down step by step, from easy to hard. How to control the screen, how to roll the input, how to create a register inside the game. 1. How to control the screen. The first step is also the simplest one. Here we need automation ribbon, ribbon writers, signal switches, and pixel packs. The setup is very straightforward. We use 4 switches, each controlling 1 bit. Write them into a signal wire bundle, and then feed that bundle into a pixel pack. This allows us to control a single pixel pack. We group 4 ribbons together and feed them into a signal distributor. Then we use 2 timer sensors to control the first and second bits of the distributor. It's important that the frequency of the first timer is twice that of the second one. This way, on the output side, we can cycle through 4 groups of signals in sequence, over and over again, using the same idea. If we add another layer of signal distributors, and set the 3rd and 4th timer sensors to have frequencies 4 times and 8 times that of the first one, we can sequentially output 16 ribbons. And here is a key point. The width of the keyboard is 16 columns. If we add a 3rd layer of signal distributors, the keyboard width can go up to 64 columns. However, I bypassed it in the 3rd layer of the distributor and retained my keyboard to be 32 columns wide, since the screen simply can't fit. 3. How to create a register in the game. This is the most difficult part. If you're not interested in the theory, you can simply look at the screenshots and copy the build directly. So first, what is our goal here? Our goal is to allow the signals coming out of the signal distributors in the previous step to propagate from right to left, 1 stage at a time, across all the pixel screens. When new input arrives, it must not overwrite or erase the previous input. At this point, we've effectively created the most fundamental concept in ACPU, memory or state preservation. In other words, we've invented a register. This concept actually exists. That's what the memory toggle does. However, the problem with the memory toggle is that it only supports a single bit of input and output. If you connect signal wire bundles to both its input and output, it performs a bitwise and operation on the 4 input bits. Similarly, we can try chaining a buffer gate and a filter gate to store a signal, but this approach also only works when dealing with a single bit input and output. There are 2 important observations here. First, and gates or gates and not gates all work on ribbons. That is, when both the input and output are ribbons, the gate performs the operation bit by bit and writes each result to the corresponding output bit. This behavior is very different from memory toggles, buffer gates, and filter gates. The second observation is that signals experience any delay whenever they pass through any logic component. We can use this delay to lock in a state. Now here's the implementation. The register is built using 2 AND gates, 3 OR gates and 3 NOT gates. To understand it, it helps to mentally divide the signals into 4 parts: the current signal, the inverted current signal, the previous signal, and the inverted previous signal. When the clock signal turns to green, the current signal is stored at the position of the middle NOT gate. When the clock returns to red, that signal is then stored in the last cycle position, creating memory. Finally, we add 1 extra OR gate purely to introduce a bit more delay, to prevent the current signal from immediately propagating into the next register. At the end, we replace all the register inputs and outputs with signal ribbons, feed them into the pixel screens, and chain the remaining registers together. And that's it. In my build I use 32 input columns, 12 pixel screens and 12 registers. The number of registers must always match the number of pixel screens. It has nothing to do with the width of the keyboard. As long as your screen is large enough, you could use 12 pixel screens to display input from a 64-128 or even to 150 6-column keyboard.